Good morning to all. Next, today's class is about the Poisson distribution. Now, the definition: the probability distribution of a Poisson random variable x representing the number of outcomes occurring in a given time interval or specific region represented as P of x is equal to e power minus lambda into lambda power x by x factorial, where x is equal to 0, 1, 2, 3, etc. up to infinity. Here lambda is the parameter. So this is the formula for the Poisson distribution. P of x is equal to e power minus lambda into lambda power x by x factorial. The value of x starts with the 0, 0 to infinity. Some of the applications of the binomial distribution. The Poisson distribution as limiting form of a binomial distribution. Already we had the explanation and definition and applications of binomial distribution. Here, the Poisson distribution is a limiting case of binomial distribution under the following conditions. Here, n, the number of trials, n is the number of trials, is infinitely large than n tends to infinity. For P, the constant probability of success in each trial is very small, then P tends to 0. If lambda is equal to NP is finite, therefore P is equal to lambda by N and Q is equal to 1 minus lambda by N, where lambda is a positive real number, which means this is the mean of the Poisson distribution and the mean of the binomial distribution. Therefore, lambda is equal to NP, hence P is equal to lambda by N and Q is equal to 1 minus lambda by N. Some of the applications of the Poisson distribution. The number of misprints on a page of a book. The number of deaths due to accident in a month on a national highway. And the number of breakdown of a printing machine in a day. The number of vacancies occurring during a year in a particular department. Some of the applications of a Poisson distribution. Next is the moment generating function, MGF. Now, Poisson distribution is the discrete random variable. So, for discrete random variable, the formula for the moment generating function mx of t is equal to summation of e power tx into p of x. Here, the value of x starts with 0 to infinity. So, summation of x is equal to 0 to infinity e power tx into p of x. So, e power tx into here, the value of P of x is equal to Poisson distribution e power minus lambda, lambda power x by x factorial. So now take the parameter e power minus lambda constant. So summation of x is equal to 0 to infinity e power tx into, so this is lambda power x by x factorial. Now, so by comparing the numerator e power tx into lambda x, we write in the form of lambda into e power t whole power x. So lambda into e power t whole power x by x factorial. We have the formula e power x is equal to 1 plus x by 1 factorial plus x square by 2 factorial plus etc. etc. Now, this form of e power x where e is equal to lambda e power t whole power x. So we can expand the value here, the formula here. Here e power minus lambda is the constant. So now e power, this is e power x. So 1 plus x by 1 factorial. So now 1 plus x by 1 factorial plus x square by 2 factorial plus etc. etc. First is here lambda e power 0. This is the value of any number power 0 is equal to 1. So 0 factorial also 1. So 1 plus, this is the next one, lambda e power t by 1 factorial plus x square by 2 factorial formula. So lambda e power t whole square by 2 factorial. So this is in the form of here e power x, where e power x is nothing but lambda e power t. So now already we have the constant e power minus t. So now in this 2 e power minus lambda into e power lambda e power t, take one e power lambda constant. So the power is, comparing these two, the powers are e power t here minus 1. So e power t minus 1. So this is the formula for the moment generating functions of the Poisson distribution. Next is the mean and variance. So now from the discrete random variable, the formula for mean is equals to, we can differentiate with respect to t from this moment generating function and t equal to 0, then we have the value of e of x. So e d by dt of mx of t. We have mx of t is equal to e power lambda I t e power t minus 1. And now differentiate with respect to t. Now here, whatever the constant we can take it outside. Here, here there is no constant. We can take the value with the e power ax. So the differentiation of e power ax is equal to e power ax into a. So we are differentiating with respect to t because t is the parameter here. So e power lambda into e power t minus 1 into differentiate power lambda is the constant, e power t minus 1 differentiation is e power t. Now put t equal to 0. So put t equal to 0 here. 0 minus 1. So e power 0. So e power 0 equal to 1. 1 minus 1 equal to 0. But anyway, the whole thing is power is 0. But anyway, e power here. So now the value of, so now lambda we take the constant outside. So lambda into e power 0 equal to 1. So lambda into 1 is equal to, here it is, so lambda. So the value of mean is equal to lambda. Next is the variance. Variance, before finding the variance, find e of x square. E of x square is differentiated with respect to t twice from the mx of t moment generative function. Already first derivative, this is the value of the first derivative, e power lambda into e power t minus 1 into lambda e power t. Now differentiate with respect to t from this mx of t. So now in this lambda is the constant parameter. Here there are two t's there. One is e power t, another one is e power lambda into e power t minus 1. So use the uv formula differentiation, u into v dash plus v into u dash. First e power t into differentiation of this e power lambda into e power t minus 1 into now e power ax differentiation is e power ax into a. So now the differentiate again the power lambda is the constant, e power t minus 1 differentiation is e power t plus v into, where the value of v is equal to e power lambda into e power t minus 1 into, here this is the next one, e power t differentiation is e power t. So after differentiation, put t equal to 0. So this is e power 0, this is e power 0, e power 0 equal to 1. So 1 into e power lambda is equal to, now 1 in here, e power 0 equal to 1, 1 minus 1 equal to 0, 0 into lambda is equal to 0, but anyway e power 0 equal to 1, and here also 1, and this is also 1, so the value is lambda. Next again substitute here, put t equal to 0, e power 0 1, here put t equal to 0, e power 0 minus 1 equal to 0. So now whole thing is e power 0, but anyway e power 0 equal to 1. So now lambda plus 1 into, already we have the constant outside lambda. So this is lambda square plus lambda, value of e of x square. Now variance of x, e of x square minus e of x the whole square. So lambda square minus lambda minus of this whole square is lambda square plus lambda minus lambda square. After we cancellation of 1 lambda square equal to lambda. Hence the value of mean is equal to lambda, and the Poisson distribution of variance also lambda. So these are the proof for the moment generative function, e power lambda into e power t minus 1. Mean of the Poisson distribution is lambda, and the variance of Poisson distribution also lambda. Next we have the problem. The first question, an average, a typist makes 2 mistakes per page. What is the probability that she will make no errors on a particular page, 4 or more errors on a particular page? So in this, first we have to identify for the Poisson distribution, what is the parameter lambda. Here, the typist makes only 2 mistakes per page. So clearly the value of lambda is equal to 2. Let x represent the number of errors on a page. Now, the formula for the Poisson distribution P of x is equal to e power minus lambda, lambda power x by x factorial, x is equal to 0, 1, 2, 3, etc. up to infinity. Now the first question, no errors on a page. So x is equal to 0. So for x is equal to 0, substitute e power, here lambda is equal to 2. So e power minus 2 into 2 power 0 by 0 factorial. Now, after we substitute, find out the solution, 2 power 0 equal to 1, 0 factorial also 1 into e power minus 2 equal to e power minus 2. The value of e power minus 2 after we calculate it is 0.1353 is the calculation of e power. First question, P of x is equal to 0. That means no errors on a page. Next is 4 or more errors on a particular page. So 4 or more errors, we can say in the probability notation, x greater than or equal to 4. So for x greater than or equal to 4, it is for a Poisson distribution, the values are always x is equal to 0 to infinity. So already we have the formula also here. X is equal to 0 to up to the last value is 0 to infinity. So better it's a shortcut notation of the greater than or equal to 4 from the probability. We can write 1 minus p of x less than 4. So 1 minus x less than 4 means below 4. So it is up to 3. Here Poisson distributions are always starts with the 0. So p of 0 minus plus p of 1 plus p of 2 plus p of 3. So 1 minus p of 0, p of 1, p of 2 up to p of 3. So 1 minus of x is equal to 0. So x is equal to 0, we have here lambda is equal to 2, e power minus 2, 2 power 0 by 0 factorial. Plus x is equal to 1, e power minus 2, 2 power 1 by 1 factorial. X is equal to 2, e power minus 2, 2 square by 2 factorial. X is equal to 3, e power minus 2, 2 cube by 3 factorial. So 1 minus e power minus 2 into here e power minus 2, e power minus 2, e power minus 2. Take the value. So 1 plus here 2 power 0, 1, 0 factorial also 1. So it is 1 plus already we took the constant outside e power minus 2. The remaining values is 2 power 1 by 1 factorial. And here the remaining value 2 square by 2 factorial. Here 2 cube by 3 factorial. So e power minus 2 into 1 plus. So now 1 plus 2 by 1 factorial plus 2 square by 3 factorial. Expand and find out the solution 0.1434. The next question. The number of monthly breakdown of your computer is a random variable having a Poisson distribution with the mean is equal to 1.8. Find the probability that the computer will function for a month without a breakdown, with only one breakdown, and with at least one breakdown. So the first of all, it is given the Poisson distribution with the mean. We have the Poisson distribution mean formula is lambda. So lambda is equal to 1.8. Here x denotes the number of breakdown of your computer. Hence the formula for the Poisson distribution P of x is equals to e power minus lambda, lambda power x by n x factorial, x values from 0 to infinity. Now first of all x is equal to 0 because without a breakdown there is no breakdown of a computer, hence the value of x is equal to 0. So if for x is equal to 0, here lambda is equal to 1.8, e power minus 1.8 into 1.8 whole power 0 by 0 factorial. So it is any number power 0 1, 0 factorial also what, e power minus 1.8, which is equal to 0.1653, the calculation, e power minus 1.8 calculation. Next is with only one breakdown. So with only one breakdown, so here x is equal to 1. So for x is equal to 1, here the formula and the lambda is equal to 1.8. So e power minus 1.8 into 1.8 whole power 1 by 1 factorial. So the calculation of this 0.2975. Next is the with at least one breakdown. So at least one, the probability notation is greater than or equal to 1. So with the shortcut notation and on behalf of x greater than or equal to 1 is 1 minus p of x less than 1. So for x less than 1 is the value of x is equal to 0. So 1 minus p of x is equal to 0. Already we have the calculation of x is equal to 0 is 0.1653 and subtract from 1 it is 0.8347 is the calculation of with at least one breakdown of your computer. Now the third question, it is known that the probability of item produced by certain machine will be defective is 5%. It is produced items are sent to the market of 20. Find the number of packets contains at least two defective items, at most two defective items in a consignment of 1000 packets using Poisson distribution. Now here it is known that the probability of certain machines are defective is 5%. So in 5% it is the probability of success P. 5% is 5 by 100, it is 0.05. Now the value of Q is equal to 1 minus P, so 1 minus 0.05 is 0.95. Here the sum of the items are sent to the market. So here it is given 20 packets, so N is equal to 20. Now we didn't have the value of lambda value. We have the mean of the Poisson distribution is equal to mean of the binomial distribution. So lambda is equal to NP, which is nothing but 20. The n value is equal to 20 into the value of P is equal to 5 by 100 is equal to 1. So we have the lambda value is equal to 1. Why we are comparing this formula? Because mean of the binomial distribution NP is equal to mean of the Poisson distribution lambda. This formula already we have. So using the formula, we have now lambda value is equal to 1. Now the first question, this is the formula for probability distribution of the Poisson distribution. P of x is equal to e power minus lambda, lambda power x by x factorial, x value is equal to 0 to infinity. Now the first question, at least two defective items x greater than or equal to 2, which is nothing but 1 minus p of x less than 2. So x greater than or equal to 2 also we can able to find from 2 to infinity. P of x is equal to 2 plus p of x is equal to 3 plus etc. up to p of x is equal to infinity. That is also possible, but anyway the shortcut formula 1 minus p of x less than 2 for p of x greater than or equal to 2. So 1 minus of x less than 2. So we have x less than 2 is x is equal to 0 and x is equal to 1. So 1 minus of, first of all, we have already lambda is equal to 1 and x is equal to 0. So e power minus 1 into 1 power x is equal to 0. So 1 power 0 by 0 factorial plus x is equal to 1 e power minus 1 into 1 power 1 by 1 factorial. And it is after the calculation, the answer is 0.2642. Now it is given whatever the calculation of first and the second using 1000 packets we have to calculate. So whatever the calculation of P of x greater than or equal to 2, just multiply by 1000 because in the 1000 packets also it is given. So multiply by 1000 in the final results. 0.2642 into 1000 equal to 264. Now in the second question, at most two defective items. For at most two defective, it is x less than or equal to 2, which is equal to, the values are starts with the 0. So 0, 1 and 2. So p of 0 plus p of 1 plus p of 2. For x is equal to 0, for x is equal to 0, already we have the lambda value is equal to 1. So e power minus 1 into 1 power 0 by 0 factorial plus e power minus 1 into, for x is equal to 1. 1 power 1 by 1 factorial for x is equal to 2. We have lambda value is equal to 1 e power minus 1 into 1 square by 2 factorial. So after the calculation of these three and added all the three values, this is the answer. So now the calculation of 1000 packets. So 1000 into the calculation of 0.9197 is equal to 920. Now, in the next heading is fitting a binomial distribution, and some more questions are there. So depends. I will submit this PPT in the. I will upload this PPT also. You can refer the remaining questions. Here, this is the simple question. In a book of 520 pages, 390 typological errors are occur. So the total pages are 520. Out of 520, only there are 390 pages. So we have a lambda, which is nothing but average. Average is just mean. So out of 520, we have error in only 390 pages. So 390 by 520 is equal to 0.75. Now the formula for the Poisson distribution, P of x is equal to e power minus lambda x into lambda power x by x factorial. X is equal to 0 to infinity. Now the first question, it is given only one question. Find the probability that a random sample of 5 pages will contain no error. First of all, we have to find one page contain no error. So the one page contain no error, it is x is equal to 0. So e power lambda is equal to here 0.75. So e power minus instead of lambda is equal to 0.75 into 0.75 whole power 0 by 0 factorial. After the calculation, e power minus 0.75. Now 5 pages contains no error. So this is p of x is equal to 0 whole power 5. Well, for p of x is equal to 0, already we have e power minus 0.75. So e power minus 0.75 whole power 5 is equal to 0.0235. This is the calculation. Therefore, 5 pages contains no errors equal to 0.0235. Now in the last question, let x be a random variable Poisson distribution such that p of x is equal to 2, which is equal to 9 into p of x is equal to 4 plus 90 into p of x is equal to 6. Sum of the relation is given. We have to find the mean and the variance using the Poisson distribution. So we have the formula mean and standard deviation. First mean formula is lambda. So we didn't have any p value, q value and any values. So lambda value, so nothing is given. So first of all we have to go for the lambda value because mean is equal to lambda. Now we can use the Poisson distribution. P of x is equal to e power minus lambda, lambda power x by x factorial, and x is equal to 0 to infinity. This is the probability distribution of the Poisson distribution. Now this is the relation. So we can write the given relation. In general, p of x is equal to 2. So for x is equal to 2, substitute in this e power minus 2 into lambda square by 2 factorial, which is equal to 9 into p of x is equal to 4. So for x is equal to 4, e power minus 9 into here, e power minus lambda into lambda power 4 by 4 factorial plus 90 into x is equal to 6, e power minus lambda into lambda power 6 by 6 factorial. So from this relation, we can divide e power minus lambda into lambda square. So for both sides, here e power minus lambda lambda square, e power minus lambda lambda square, e power minus lambda lambda square we can divide equally for both sides. So the remaining is 1 by 2 factorial is the LHS, which is equal to 9 into, after we divide e power minus lambda into lambda square, it is lambda 9 lambda square by 4 factorial plus 90 into, after we divided this e power minus lambda into lambda square, so the remaining value lambda power 4 by 6 factorial. So the calculation, after the calculation and simplify, after factorize the equation lambda power 4 plus 3 lambda square minus 4. So we have lambda values are 1 and minus 4. Lambda value, which is the parameter mean, is always positive. So we can neglect the second value. So lambda is equal to 1. Hence the formula for mean is equal to lambda. Lambda is equal to 1. The second question is standard deviation. Standard deviation, which is nothing but variance. Square root of variance is the standard deviation. Already we have the formula for variance of the Poisson distribution also lambda. Hence lambda is equal to 1. Mean is equal to lambda and the variance also lambda. The question is standard deviation. So square root of variance. So square root of 1 is equal to 1. Now the last question is the fitting Poisson distribution. So the given data are x is equal to 0, 1, 2, 3, 4, 5 and f is equal to 142, 156, 69, 27, 5 and 1. Now we have to use the fitting Poisson distribution. Find the probability mass function, then find the theoretical frequencies. So this is the formula. Poisson distribution formula. P of x is equal to e power minus lambda into lambda power x by x factorial. X is equal to 0 to infinity. So the given data are x is equal to 0 to 5 and also the given frequencies are 142 to 1. That means x is equal to 0, f of x is equal to 142. And so on, x is equal to 5, f of x is equal to 1. Now we should find fx because mean, which is nothing but average is equal to sigma fx by sigma fx. So after we finding the average, which is nothing but the value of mean. Hence here, so average is sigma fx. So just multiply 0 into 142, 0, 1 into 156, 156, 2 into 69, 3 into 27, 4 into 5 and 5 into 1. So 1 into 156, 156, 2 into 169, 138, etc. up to the last value. Hence, mean is equal to lambda for the Poisson distribution, which is nothing but average. Average, we have the formula x bar is equals to sigma fx by sigma f. So we have sigma fx is equal to 400. So 400 by 400 is equal to 1. So this is the calculation of the average of this table, which is nothing but lambda. Lambda is equal to 1. Now we have the total is equal to 400. So here capital N is equal to 400. Now we can proceed for the theoretical frequencies. We have the formula Poisson distribution e power minus lambda into lambda power x by x factorial. This is the value of p of x. Here we have n is equal to 400. So n into p of x. So n is equal to 400. 400 into formula. First of all, there are values are given x is equal to 0 to 5. For x is equal to 0, x is equal to 1, x is equal to 2, x is equal to 3 and x is equal to 4 and 5. Substitute all the values in the formula here. For x is equal to 0 here, e power minus 1 into 1 power 0 by 0 factorial. So after the calculation it is 147.15. Now for x is equal to 1 is the second data. For x is equal to 1, substitute here e power minus 1 into 1 power 1 by 1 factorial. So after the calculation of this and multiply by 400, we have 147.15. And the next data is x is equal to 2. For x is equal to 2, substitute in this. Now 400 into x is equal to 2. So 400 into for x is equal to 2. Here e power minus 1 into 1 square by 2 factorial. And x is equal to 3 multiplied by 400. Now e power minus 1 into 1 cube by 3 factorial and multiply by 400. And for x is equal to 4 here, 400 into e power minus 1 into 1 power 4 by 4 factorial, it is equal to 6.13. And for x is equal to 5 here, substitute e power minus 1 into 1 power 5 by 5 factorial and the calculation is 1.23. Now the final answer, we have to write all these values in the table after we round off. So for example, 147.15, after we calculating the round of whole value, it is whole number is 147. So the whole number of 147.15 is 147. It is here for x is equal to 2 is 73.5 is after we round off the value it is 74. So for 24.5 it is 25. For 6.13 after converting into the whole number it is 6. For 1.23 after we converting into this 1. So after the adding the total theoretical frequencies are, so 147 plus 147 plus 74 plus 25 plus 6 plus 1 is equal to 400. This is the theoretical frequency of F, and for given totaling of F also 400. So the given totaling of the given frequency 400, which is equal to our theoretical frequencies of the calculation of 400. Hence both the answers are verified. Hence our fitting is satisfactory. Therefore the binomial fitting of the given table, the given question is satisfactory. This is the beauty of the fitting by Poisson distribution of this table, hence verified. Thank you all.